everyone. Today I would be giving you all a presentation on the interference of light, and we would come to know how interference takes place. Now, we all know that there are two schools of thought regarding the interference of light: the corpuscular theory, which was propounded by Newton, and the wave theory, whose propounder was Huygens. And all of you know that from corpuscular theory, the rays move like in corpuscles, as propounded by Newton. They crisscross, but they do not superpose to give interference pattern. The phenomenon of reflection and refraction can be explained by this theory, but interference, diffraction, polarization could not be explained. Now, this was further studied by Huygens, who showed that if we take the wave nature of light, the movement of uh, light in the form of the rays in the form of wavefront or wave trains, then we can justify superposition of waves in the region of crossover like any other wave. Now, this superposition results in interference. However, there is condition for sustained interference. Now, uh, the conditions, as all of us know, is that the rays should be coherent. The rays, interfering rays, should have same frequencies. The rays should have nearly same or equal amplitude. They must originate from point source or narrow source for interference by division of wavefront. They must originate from extended source for interference by division of amplitude. And to obtain good contrast, the background should be dark and the intensity of minima should be zero. Now, well, we know that Thomas Young was the first scientist and the propounder of interference pattern by division of wavefront, and we all know how he had done his experiments. The figure aptly shows that light comes out from the source, coming out from a point source, passes through two pinholes as slit 1 and slit 2, and then as the wavefronts interfere, as you can see from this figure, we get alternate dark and bright fringes. All of you know by now that the to satisfy constructive interference, the path difference should be as it's given over here, and to satisfy destructive interference, well, this is the path difference. This actually gives us equal fringe width. Okay, fringe widths are same for both bright and dark fringes, but the interesting point of the whole thing is that if we shift the screen, then the fringes are formed at some other points, and therefore these fringes are not localized fringes but non-localized fringes. Now, the other interference that we see is that through thin film, and that the propounder of that particular study is Robert Hooke and Isaac Newton. Are now here, as the figure shows, that you have incident ray falling on a medium, part of which is reflected and part refracted. The refracted beam, after reflection, comes out and interferes, giving you interference pattern from reflected ray. Similarly, we can have interference pattern from transmitted ray, and the path difference obtained is the sum of the path difference of these two rays minus the path difference here, and the conditions are just the opposite of what we have obtained from Young's double slit experiment. It is this as given for constructive interference and this for destructive interference, provided we are considering interference of reflected components. The conditions are just the opposite for transmitted components, and we all know that this takes place by division of amplitude. Here the figure aptly shows that a phase change of pi takes place when the reflected ray from a lighter medium, it gets reflected from a denser medium. Now, when we make a comparison of the interference by division of wavefront and amplitude, you see these are the following experiments that one performs. few such experiments like Young's double slit, Fresnel biprism by division of wavefront, whereas Newton's ring and all interferences on source films are by division of amplitude. We know that interference by division of wavefront are through a narrow source or a point slit source, narrow slit source. Here it has to be essentially through extended sources. The fringes, if we see, are hyperbolas. If we just solve them, the path difference is small and the eccentricity is large, and so they appear as straight lines. Whereas here, the fringes are circular for wedge-shaped film. Well, the condition for constructive and destructive interference is same as that for interference from transmitted light by division of amplitude, whereas here the condition for constructive and destructive interference from reflected light is opposite to that of transmitted light. So it's opposite to that what we see from division of wavefront. Here we obtain from division of wavefront fringes of equal thickness, but here in Newton's ring we do not obtain fringes of equal thickness, but essentially here also we can obtain fringes of equal thickness as well as fringes of equal inclinations. And these fringes are actually localized fringes, whereas these are, as I have already pointed out, they are non-localized fringes. Well, you students, it's important to remember some of the important formulas for solving problems, of which I have written down the formulas for constructive interference and that of the fringe width. And here the angular separation, if you need to calculate for an mth order, you can do it in this manner. Whereas for division of amplitudes, these are some of the important formulas. These formulas are for bright and dark fringes of Newton's ring. The symbols have their usual meaning. Now, a very common question that comes up is the engineering application of interference. Well, this is well applied eh, for getting effective interference. We actually use anti-reflective coatings. Now, these coatings are so made such that the reflected light observed actually is such it is reduced by a large amount so that a major portion of the light is not reflected but transmitted, and use of this and this actually this is possible if the refractive index of the anti-reflective coating is more than that of air but less than that of the refractive medium through which the beam passes, and this actually ensures that we get complete interference, constructive interference, or complete destructive interference. Interference can be made completely constructive or destructive by using the anti-reflective coating, and it serves many important purpose and has very large engineering of applications. Now students, the important thing is uh, what many of us do not know is what interference do we observe in nature. Well, the thin film interference is also observed in nature. In We observe it in the wings of the peacock. The wings are so thin that some of the light rays which passes through the thin film are reflected in such a manner and some absorb that it gives that beautiful color in peacock's ring. Also, the color of the butterfly's wings and some of the colors of flowers are also due to the reflections from thin films and interference taking place from there. So, looking into the nature also, we observe application of thin films and beautiful play of colors. So thank you students. I hope all of you will read further work in internet and find out more on engineering applications of interference and also utility of anti-reflective coating. Thank you. Thank you very much.